In this video, we'll introduce the idea of slope fields or directional fields. Sometimes it can be impossible to solve differential equations in the sense of obtaining an explicit formula or a solution. And so we need a way to come up with an approximate solution or a general solution. Slope fields will allow us to do that. Keep in mind that dy dx is really just the slope. So we can think of the slope of this as x plus y. What we're going to do is we're going to calculate the slope at multiple different points to get an idea of the general look of the solution. We can do that more easily with a table. Keep in mind again, the dy dx is really just m, so really we're just adding x and y. And I've got a grid here with values for x. Let's make the top x and the vertical values y. And we're simply going to add these x and y values to get a slope at that specific point. Now you can start anywhere you want. I think it's easiest to find a place where we have zeros. For example, 3 plus -3 would be 0. And the next one where we have 0 would be 2 plus -2. That would be 0. And you might start to see a pattern. We have 1 and -1. And that entire diagonal is going to be zeros. And then we can just choose another spot from there. Say 2 plus -3. That would be -1. 1 and -2 add to -1. And again, that -1 pattern is to continue. Next, we have 1 plus -3. That's going to give us -2. 0 plus -2. Again, we see a pattern here. That diagonal is going to be -2's. And we'll just continue this process. 0 plus -3. Here we get a diagonal of -3's. And -1, -3 will give us -4. Continue that pattern. Then we get -5 on this diagonal and -6. And then coming down here, intuition tells us it'll probably be 1. Let's double check. We have 3 plus -2. That gives us a 1. And again, confirm 2 plus -1 is also 1. That pattern will continue. So it's a little tedious, but there are some patterns that we can follow to make the process a little bit easier. 3 plus -1 is 2. 3 plus 0 is 3. And again, we'll just continue this pattern to help fill out the table. Once we have all of these values filled out, make sure you recognize that these are slopes at given points. So what we're going to do next is we're going to go to each of those points and draw a little line that represents the slope of the curve at that specific point. I like to start at the zeros. For example, -3, 3. That has a slope of 0. So we have -3, 3. At this point, the slope will be 0. So we're going to draw a small horizontal line there. And then just be very careful when we're going to the next one. Make sure your x's and y's are correct. We have -2 for x, +2 for y. So that's going to be here. And again, that pattern will go across the diagonal. So we have -1, 1. And we'll just continue that pattern, getting those horizontal lines. Up next, let's say we wanted to go to -2, 3. It has a slope of 1. -2, 3 here has a slope of 1. So that's going to look something like this. Again, that line has a slope of 1. The next one we have is -1, 2. negative 1, 2. This has a slope of 1. And again, we will continue that pattern with that slope of 1. Up next, we have a slope of 2. That's at negative 1, 3. So at negative 1, 3, we have a slope of 2. That means that line is going to be a little bit steeper this time. And again, go along the diagonal. Then we have 0, 3 has a slope of 3. So 0, 3. We have a slope of 3, again getting a little bit steeper. It's a little bit hard to do these by hand. We have 1, 3 has a slope of 4. Again, getting a little bit steeper. And then we have a slope of 5 and 6. And then along this diagonal, negative 3, 2. Negative 3, 2 has a slope of negative 1. So that's going down this way. And that diagonal continues to have a slope of negative 1. Negative 3, 1. Negative 3, 1 has a slope of negative 2. So again, negative slope, just a little bit steeper. And that continues along the diagonal. Negative 3, 0 has a slope of negative 3. So again, getting a little steeper along this diagonal. Then negative 4, negative 5, and negative 6. And so it's not perfect. If we wanted to get a better slope field, we could use some graphing software. But for now, we'll just do this simple example by hand, just to give you an idea of what a slope field looks like. Keep in mind that this is just a general solution to the equation. If we wanted a more specific solution or specific answer, we would need more information. We would need an initial condition. For example, let's use the directional field that we have to find a solution that passes through the origin 0, 0. At 0, 0, we have this horizontal tangent line, which means we're looking at a maximum or a minimum. In this case, it must be a minimum. If we look at the direction field, there's going to be a min there. And if we look at the left side of that, notice we have kind of an asymptote here with those slopes of negative 1. So we can draw the left side. It's going to look something like this. We'll come down and hit that min. And then as we go to the right, we have a slope of, let's see, that was a slope of 2, I believe. And then it's just going to get steeper and steeper as we go along. So this would be a sketch of the solution with the initial value 0, 0. What if we wanted to sketch the curve that passes through negative 2, negative 2? This time we're looking at negative 2, negative 2. So we're looking at this point. To the left, it looks like we're starting out fairly steep, coming down, going through negative 2, negative 2, and our solution looks something like that. Up next, we have 2, 1. Let's look at what happens when we go through 2, 1. This time, the initial condition is 2, 1. On the right side, we have something like this. As we approach the left, it looks like we're getting close to a minimum and then going over to the asymptote. So at some point down here, it's going to hit a min. and then it'll follow that -1 slope. So this is the solution where we're looking at an initial condition of 2, 1. And let's maybe do one more example. Let's say we wanted to go through 1, -2. So if we're going through 1, -2 down here, notice that that is on that slope of -1, kind of an asymptote there. So that's just going to go through that slope of -1. And again, these are specific solutions with initial conditions that fit the slope field. This was a relatively simple example that we did by hand. More complicated examples will use technology to help us graph these slope fields. In this example, we want to match each differential equation with the corresponding direction field. Now, we could use technology to do this, but let's see if we can do this without using technology and using what we know about slope fields. You'll have to bear with me with some of the scrolling, and we'll have to scroll back and forth to look at some of these. Up first, let's see if we can match graph A. I like to start with a derivative of 0. I think that horizontal tangent line is easy to identify. So in this first one, if we want y prime to be 0, that means y would have to be 2. So let's look for horizontal tangent lines along y equals 2. That happens here, but it also happens down here. We have those horizontal tangents along y equals 2. So we need some more information. We could think about it this way. Notice that you don't see the x variable in this equation. The slopes at each point are independent of x since x isn't there. So that means that at every point that is parallel to the x-axis, we should have the same slope. So in this example, we are parallel to the x-axis, but notice that the slopes are not the same. Whereas if we go down here, notice that this line is parallel to the x-axis and all of those slopes are the same. Same thing here, we're parallel to the x-axis and all of those slopes are the same. So here we have A. So part A was graph 3. In part B, again, I like to think of the derivative being 0. So that's going to happen when x is 0, right? When x is 0, or when when y is 2. If y is 2, we have a y prime of 0. So let's look for the x equals 0, that's the y-axis. So do we have horizontal lines on the y-axis anywhere? Notice in graph A, it looks like we do have horizontal lines on the x-axis. We also want horizontal lines on y equals 2. We have that here as well. So it looks like that's probably going to be the case. If we wanted to be certain, we could pick another point, say 1, 1. If we plug in 1, 1 for x, y, that will be 1 times 2 minus 1 is 1, so y prime is 1. So at 1, 1, we should have a slope of 1. So let's see, 1, 1 is here, and it looks like we do have that diagonal, that 45-degree line, so it looks like it's that one. So this B would be 1. In part C, again, I like to find out where y prime is 0. So let's just make it equal to 0 and see if we can solve for y. So if we get y equals, that'll be negative x plus 1. So anywhere along the line y equals negative x plus 1, we should have a horizontal tangent, those horizontal tangent lines. So let's see what happens here. So we already looked at 0, 1. Looks like y equals negative x plus 1. That's going to be this diagonal. It looks like those are not horizontal tangents there. Let's see if it is here. Yeah, so here we go. Y equals negative x plus 1. It looks like we do have horizontal tangents along that line. So it looks like this is the part C. And then just to confirm, let's check part D. Part D should be with graph 2. Let's see where y prime is. Y prime is 0 when x is 0 and when y is 0. So let's see. That's the x-axis and the y-axis, and it looks like those do have horizontal tangents. It's somewhat hard to see that the x-axis has horizontal tangents, but it's there. And the y-axis, we can see that that does have horizontal tangents. So we have x equals 0 and y equals 0 will give us y prime of 0. That must be graph 2.